JMB, how are you all? I hope you all are good. I welcome you all to my YouTube channel. My name is Prince Ranpara. I am a PhD scholar in the Department of Chemical Engineering at the Indian Institute of Technology, Ropar. So in today's lecture, we will understand how we derive the design equation of the packed bed reactor. Right? So let's get started. So the first question which arises in our mind is, what is packed bed reactor? Okay. The second question which arises in our mind is how the packed bed reactor differs with the other industrial reactors. The third question which arises in our mind is what are the significant importance of the packed bed reactor in the industrial applications, right? So you'll understand all these things, right? So let's get started. So first of all, we'll understand the term packed bed and reactor, right? So first of all, we'll understand the term reactor. So reactor, which means here you can see. So this figure here, this figure demonstrates the diagram of the packed bed reactor, right? So reactor, which means reactor are the here you can see the rectangular black outlines of the reactor, right? So the rectangular black outlines of the reactor, which means is uh, the volume which is enclosed by the system by these reactor boundaries are called the is called the reactor, right? And inside the system volume, inside the reaction environment where the reaction takes place. Okay, I hope you have understood the term reactor. Now we'll understand the term bed, right? What the term bed means. Okay, now bed means, so now before diving into the understanding of the term bed and packed bed, we'll understand the principal difference between the plug flow reactor and the packed bed reactor, right? So the principal difference between the plug flow reactor and the packed bed reactor is the homogeneous phase system and the heterogeneous phase system, right? In the plug flow reactor, the reactions are carried out in the homogeneous phase system, right? And in the case of packed bed reactor, the reactions carried out by using the packed bed reactor are the fluid solid heterogeneous systems, right? Where the fluid will interact with the solid catalyst, solid support, or solid inert materials, and the reaction will takes place. Okay. So in the case of plug flow reactor, we'll have the fluid split systems where the reaction will take place, right? And reactants will get converted into the new products. But in the case of packed bed reactor, we'll have the solid catalyst or solid support or solid inert materials present inside the hollow space of the packed bed reactor, right? So we already know that the plug flow reactor is a tubular reactor, right? A tubular reactor in which we have the hollow space inside the reactor. Okay, it's called the plug flow reactor, right? But here in the in comparison with the plug flow reactor, in the case of packed bed reactor, where the hollow space of the tubular reactor is being filled with the packing materials, right? The packing materials can be a solid catalyst, a solid support, or solid inert materials, right? Which means now, which means the hollow space. Okay, so for, the packed bed reactor is also known as the fixed bed reactor, right? So bed. Now we'll come back to the term bed, right? So what does the term bed means, right? So let's say here we are having the tubular reactor. Now in the case of PFR, we have the hollow space, right? So here we were having the hollow space in the tubular reactor, which was known as the plug flow reactor. But in the case of packed bed reactor, the tubular reactor is filled completely with the packing materials, right? Different types of packing materials, right? It may be a solid catalyst, a solid support, solid inert materials, or any solid phase, right? So we'll try to generate a bed inside the tubular space where the entire hollow space of the tubular reactor will be filled completely with the packing materials, right? It's called the bed. So we'll try to generate a bed of the solid phase inside the hollow space of the tubular reactor. It's called the bed, right? We'll try to generate the bed inside the reactor. Now we'll understand both the terms together. Packed bed, right? So packed means what? Packed means we are filling the we are filling this space completely in order to occupy entire hollow space, right? It's called the pack. We are tightly packing, we are uniformly packing, right? Okay, now packed bed means what? Packed bed means in the packed bed reactor, in the tubular reactor, we have the hollow space, right? Now hollow space we are completely filling with the Packing materials may be a solid support, a solid catalyst, a solid inert materials, or any solid phase, right? So this is here this is the system volume. Reactor boundary, the reactor boundaries which enclose the system volume, it's called the reaction environment, right? System volume. So in this system volume, where we'll try to completely fill the entire volume of the tubular reactor with the packing materials, right, with the solid support, with the solid catalyst, right? So here you can see the blue circles. Here you can see the blue circles, right? The blue circles indicates the different packing materials, right? So entire hollow space of the reactor, we are trying to uniformly distribute, we are trying to uniformly packed entire hollow space of the reactor with the solid catalyst, with the solid support, with the solid inert materials, right? It's called the packed bed reactor. I hope you understood. Okay. So we need to ensure the packing of the solid catalyst or the solid support or the solid inert materials to be uniform throughout the entire volume and the length of the reactor, right? So it's called the fixed bed, which means now we have completely filled the entire hollow space with the solid materials, right? Solid catalyst, which means it is fixed, it cannot move, right? It is a stationary state. It is in a stationary state. The packing materials are in a stationary state, which means it's called the fixed bed, right? It is fixed, now it cannot move. Okay, so for those reasons, the another name of the packed bed reactor is fixed bed reactor, right? Now we'll dwell more deeper into the understanding of the packed bed reactor, right? So let's say this diagram represent the packed bed reactor, right? Here we have the reactor boundary indicated by the rectangular black line, right, in the reactor boundary which enclose the system volume. Okay, in the system volume, in the reaction environment where the reaction takes place. So here you can see the inlet path, right? So this is the inlet portion from where the reactants enter through the inlet stream into the packed bed reactor, right? And here in this portion where you can see we have the exit portion, right, outlet stream. So from the outlet stream, the product will exit through the outlet stream. Okay, I hope you understood. Now let's say we'll understand that here you can see that the entire hollow space of the tubular reactor is filled with the packing materials, with the solid catalyst, which is indicated by the blue circles, right? So here in the entire packed bed reactor, all the blue circles indicate the solid catalyst, completely filled with the solid catalyst, right? The entire hollow space of the reactor is completely filled with the well distributed uniform solid catalyst, solid support, solid inert materials, or any solid phase, right? Okay, I hope you understood. Now what will happen through the inlet stream? Now here we are having the solid phase present in the reactor system, right? And now we will send the fluid, we'll feed the fluid from the inlet stream of the packed bed reactor. So we in the packed bed reactor we'll have the fluid solid interaction, right? So fluid solid, so there will be the reaction between the fluid and the solid catalyst. Okay, and the reactants will get converted into the new products, right? So what will happen, the reactants here, all the dotted red dots you can see are the reactants. Okay, so we need to ensure the uniform packing in the entire hollow space of the packed bed reactor. And second thing, we need to also ensure in the ideal, so this is the ideal case of the packed bed reactor, right? So in the ideal case of the packed bed reactor, we need to also ensure the uniform distribution of all the entire reactant molecules throughout the volume and the length of packed bed reactor, right? So here you can see these red dots indicates the reactants, right? So these all the fingertips which indicates the reactants. So your reactants should be, the reactant molecules should be uniformly distributed throughout the entire volume and the length of the reactor, right? I hope you understood. Now let's understand how the reaction will take place in the packed bed reactor. Okay, so here you can see the red dots indicates the reactants. Now reactant will enter into the packed bed reactor through the inlet stream, right? So FG0 indicates the initial molar flow rates. Initial molar flow rates, which means the initial molar flow rates of any chemical species which is entering into the packed bed reactor. It's indicated by FG0, reactants, right? Okay. Now the reactants will enter into the reactor. So in this portion, in this plug, you can see we have the red dots, right? Major amount of the red dots, which means, and which are interacting with the solid catalyst with the blue circles, right? So all the blue circle indicates the solid catalyst. Okay. So the reactants molecules will interact uniformly with the solid catalyst present in the backbed reactor. Okay. Now, when the reactants molecules will interact with the solid catalyst, the reaction will take place, right? And will get converted into the new products, new byproducts, intermediates, and unreacted reactants will remain, right? And the products will get generated. Okay. So what will happen? We have the uniform distribution of all the reactants, and the reaction will take place with the reactant molecules and the solid catalyst, and will get converted into the new products, which is indicated by the new chemical species, which is indicated by green dots, right? So here in this portion, you can see the transformation of the red dots into the green dots, right? In these green dots, you can see where the new chemical species has generated. Okay. Now further, as we move along the length and volume of the reactor, right? As we move along the length and volume of the reactor, the reaction will take place between the solid catalyst and the reactant molecules, the chemical species, right? So from green chemical species, now here in this portion you can see we have the black dots, right? Major amount of the black dot, which means a new chemical species is formed here, right? The new chemical species may be intermediate species, transition species, or any byproducts, or maybe products, right? Okay. So in again, now as the reaction progress, as the time progress, these chemical species will get converted into the new chemical species, which is indicated by the blue dots, right? So here we are having the major amount of the blue dots, right? Likewise, here with the progress of the reaction, these chemical species will get transformed into the red and black dots, right? So here new chemical species has formed in this plug, right? In this plug, the new chemical species has already formed, right? So likewise, when we come to the end of the plug packed bed reactor and towards the end of the completion of the reaction, now what will happen in this portion, where you will see we'll have the major amount of the green dots, which indicates the formation of the products, right? So green dots indicates the formation of the new products, desired product, right? So what will happen? So with the completion of the reaction, the desired product will get generated in the reaction environment and will get exit through the outlet stream, right? So here in the outlet stream, you can see we have the major amount of the green dots, which represent the formation of the desired product during the run of the reaction, right? So in the desired product, where you can also see the presence of trace amount of blue dots, red dots, black dot, which means those are the unreacted. Those from those where we have some trace amount of unreacted reactants, byproducts, intermediate chemical species, and the products, right? So but the major amount will have the desired product, right? So likewise the reaction will take place. I hope you understood. Okay. So in order to make you simple understand, you can visualize here. See the black boundary of the reactor indicates the reactor boundaries, and the blue the hollow space in which we have filled the entire packing materials, right? Filled with the solid catalyst, right? So the blue circle indicates the solid catalyst, right? Now the reactant will enter through the entire hollow space and will react with all the solid catalyst uniformly, and the conversion of the reactants into the new products will take place, and finally the product will exit through the outlet stream, right? I hope you understood. Okay, now we need to also understand the assumptions of the packed bed reactor, right? So we have the similar assumptions as of the plug flow reactor. So all the assumptions of the plug flow reactor will be applicable to the packed bed reactor, right? So we'll recall the assumptions, right? So as the first assumption, we should have the steady state condition, which means there will be no accumulation of any chemical species inside the reaction volume. Okay, which means there are no chemical species which are getting accumulated inside the reactor, right? So all the chemical species are exiting the reactor through the outlet stream, right? It's the first assumption, due to which accumulation term is equal to 0, and we are having the steady state conditions, due to which the accumulation term dnj by dt will be equal to 0, right? Okay, the second assumption is like the molecules which are exiting from the outlet stream will not mix with the molecules which are entering from the inlet stream of the packed bed reactor, right? Again, the molecules which are exiting through the outlet stream of the packed bed reactor will not mix with the molecules which are entering through the packed bed reactor, right? Which means there will be no axial mixing, right? There will be no axial mixing, which means the molecules will not mix with each other in the axial direction, right? I hope you have understood. But there will be radial mixing, which means from the here we have the axis, right? So from the axis in the radial direction, from in the above radial direction and the below radial direction, all the molecules can mix with each other, right? Which means due to the radial mixing, we'll have the uniform distribution of the concentration. Okay, so with respect to the axial position, we have the uniformly mixing in the radial direction, which means due to the radial uniform mixing in the radial direction, we'll have the uniform concentration, uniform temperature, uniform pressure, and uniform rate of the reaction, right? But as the axial position will change, there will change in the concentration, reaction rate, and the temperature and the pressure. But in that new axial position, entire radial direction will have the uniform concentration, temperature, and pressure, right? It is tricky. I hope you understood, right? Okay, so with respect to that, which means which means along the entire radial direction we'll have the uniform concentration, uniform temperature, reaction rate, pressure, right, with respect to the each and individual axial position. But here's the axial position will change. There will be the change in the concentration, temperature, pressure, and the rate of the reaction, right, with respect to the axial position, right? Okay, so I hope you have understood, right? But with the specific axial position, let's say with the specific axial position, will not in the radial direction will not have any gradient in the concentration, temperature, pressure, right, and the rate of the reaction, which means in the at this specific axial position will have the uniform distribution of all the reaction parameters, right? I hope you have understood. So now by using the universal general mole balance equation, we'll try to derive the design equation of the packed bed reactor, right? So let's get started. So we already know the universal general mole balance equation, which is the rate of flow of J into the system, right, is indicated by Fj naught minus the rate of flow of J out of the system, which indicated by Fj are the molar flow rates, right, plus the rate of generation of any chemical species in the reaction environment is indicated by the generation term will be equalized to the rate of accumulation of any chemical species in the reaction environment, right? Which means if there are any possibilities of accumulating any chemical species inside the reactor, or there is no accumulation of any chemical species, which means all the chemical species are exiting through the outlet stream. Okay, which means we have this steady state condition. Accumulation term will be equalized to 0, right? So in minus out plus generation is equal to accumulation, right? So inlet can be written as Fj naught, initial molar flow rates. Outlet can be written as the Fj or the final molar flow rates, plus generation term Gj is equal to accumulation term dnj by dt, right? So here the second equation where we have the Fj naught as the inlet minus Fj as the outlet flow rates plus integration of Rj into dw is equal to dnj by dt. Okay, now how the dw came, right? So we'll understand that. So in order to understand the deriving of the packed bed reactor, we need to consider the differential elements, right? So with the entire volume of the reactor, we have filled with the solid catalyst, right? So we'll consider this part as the differential element in order to derive the design equation, right? So at this part where you can see at this position, we have the uniform molar flow rate as Fj at this position where we'll have the certain weight of catalyst, right? So let's say here at the starting point where the length is equal to 0, we'll have the volume, initial volume, it will be equalized to 0, right? In the initial volume, which has the the volume which has the presence of mass of the catalyst, right, is indicated by W, right? So is equalized to 0 because it is the inlet part, right? But after some length in the volume of the reactor, we have some amount of catalyst which is present, right? So up to this position where we will have some amount of catalyst which is present in the bed reactor is indicated by W. W represent the weight of the catalyst which is present at this position, right, where the molar flow rate is Fg, inlet part. Here we'll consider this differential element for the deriving of the design equation, right? Now same way at the outlet part of the differential element, right, differential element where we'll have the same uniform molar flow rate Fj, but the weight of the catalyst will be W plus delta W. So delta W will so here the delta W represent the certain amount of catalyst which is filled in this differential volume, and across this differential volume we'll try to derive the design equation of the bed reactor, right? So the W is here, so delta W, so W plus delta W will be here. So up to this position we have W plus delta W mass of catalyst which is present in the bed reactor, right? I hope you have understood. Okay, so for those reasons we are considering as integration of Rj into W delta W, which means with this differential element of the delta W, the rate of generation of any new chemical species will be indicated by delta Gj, right? Delta Gj. I hope you understood, right? So for those reasons we can write as the integration of Rj into delta dW is equal to the acclimation term dnj by dt, right? And the delta Gj can be written as the integration of Rj into dW is equal to Rj into delta W, which means the generation term is the product of the rate of the reaction, rate of the formation, with respect to the differential weight of the catalyst, right? Differential amount of the catalyst present in this differential element. Okay, now we are considering the steady state of conditions, which means acclimation term will be equalized to 0. Therefore the dnj by dt is equalized to 0, right? So we'll put both the values in the Reynolds mole balance equation, right? So in the fourth equation we are writing the inlet molar flow rate as Fj naught. So here we'll write the inlet molar flow rate as Fj with respect to the W, right? So Fj at the position where we have certain mass of the catalyst present in the bed reactor, inlet term, right, minus outlet term Fj. We are having the similar molar flow rates, right, at the position where we'll have the certain mass of the catalyst which is W plus delta W present in the bed reactor, this mass, right? So Fj at W plus delta W, okay, plus the generation term and equalized to the acclimation term. I hope you understood how we derive the fourth equation, right? Now we are trying to rearrange the equation. Okay, so Rj delta W, we are trying to make the subject of Rj delta W, right? So we'll shift the Rj delta W to the right hand side. Now shifting the Rj delta W term to the right hand side, then the sign convention will change from positive to negative, right? So for those reasons, here we can see, here we are having the Rj delta W on the right hand side, due to which we have the negative sign, right? First of all, it was having positive sign, okay, and this will remain as it is, right? Fj at W minus Fj at W plus delta W is equalized to minus Rj delta W, okay. Now we are making the subject as Rj. So in order to make the subject as Rj, we need to multiply this equation with the negative sign, right? So multiplying this equation by negative sign and dividing the entire equation by delta W, okay, so will result into this final differential equation, right, which represent Rj is equal to, so here if we are multiplying with the negative sign, now what will happen? Here we have the positive sign, right? So minus, negative sign we are multiplying with the positive sign, so minus plus, this will become negative. So for those reasons we are writing minus Fj at W, and here we are having already minus negative sign is present. So if we are multiplying with the negative sign, so minus minus plus, right? So we have the Fj at W plus delta W minus Fj at W, and we are dividing the entire equation with the delta W. So we'll obtain the final equation fifth, okay. So the equation fifth represents the difference quotient, which means the average rate at which the molar flow rate changes with respect to the volume and the length of the reactor, right? So here we have the, with respect to the amount of the catalyst filled with respect to the volume and the length of the reactor, how the molar flow rate will change, okay. It's understood by the difference quotient, okay. And we have already understood how the reaction rate and flow will vary with respect to the reactor volume and length and mass of the catalyst present in the backbed reactor, right? If you want to recall, I request you to please watch the previous lecture, lecture number 8. Okay, so we already understood this. Now, in order to convert the difference quotient equation 5 into the final difference form, we'll try to apply the limit delta W tends to 0, which means the differential element, the any small differential weight of the catalyst will tends to 0, which means we are dividing the entire weight of the catalyst into a very small, infinitely small parts, right? Infinitely small parts. For example, the entire volume of the reactor is filled with the 10 gram of catalyst, right? So entire volume and the length of reactor, we have the 10 gram of catalyst present in the backbed reactor. Now we are dividing that 10 gram, first case, now we are dividing that 10 gram into 10 parts, which means the one individual part will consist of the 1 grams, another part will consist of the 1 grams. Likewise, 10 parts we have, so 10 grams, right? In the another second case, if we are dividing into a very small, infinitely small part, which means, let's say, similarly, we have the 10 grams of catalyst present in the backbed reactor. Now we will divide that 10 grams with the 1 lakh parts, which means 10 divided by 10 grams, we are dividing into 1 lakh part, which means 10 divided by 1 lakh, which means the answer will be 0.0001, 0.0001, which means the weight of the infinitely small part, which will have the weight of 0.0001 gram, right? Which is very small. So delta W, the infinitely small part delta W will tend to 0, because the delta W is equal to 0.0001. So it tends to 0. So in order to neglect all the errors, right? So we are applying the limits in order to neglect all the errors and in order to make the calculations perfect, right? Up to certain values, right? Perfect. Okay, so we are applying the limit delta W tends to 0. Okay, so Fj at W, so we'll write the same equation, but we are now applying the limits. So limit delta W tends to 0, Fj at W plus delta W minus Fj at W upon delta W is equal to Rj, right? Now this final differential form can be converted into the differential form, which represented by the equation 6. Rj is equal to dFj by dW, which means Rj is the rate of the reaction, which means how the molar flow rates of chemical species will change with respect to the volume, length, and weight of the catalyst present in the backbed reactor, right? Now, in order to derive the design equation of the backbed reactor, we will derive with respect to a reactant, right? Species A. So here the reactant is a species A, right? So Rj can be written as minus Ra. Why minus Ra we are writing? Because during the progress of the reaction, during the run of the reaction, the reactants will get consumed and will get converted into the new products, right? So due to the disappearing of all the reactants from the reaction environment, the reactants will get consumed, the reactants will get disappear from the reaction environment, and the reactants will get converted into the new products, right? So for those reasons we are writing minus Ra, right? So minus Ra is equal to dFA by dW, right? dFA by dW, change in molar flow rates of reactants with respect to the weight of the catalyst present in the entire volume and the length of the reactor, right? Now we are making the subject as dW, so dW is equal to dFA upon minus Ra. Okay, now finally we are integrating the equation 7 on the both the sides, which means we are integrating. Now why we are integrating? Because in order to make the summation of all the infinitely small parts, right? So we'll have the good accuracy value, right, with the minimal or zero error, right? So integration on the, we are applying the integration at the both the sides. So integration of dW from limit 0 to W is equal to integration from initial molar flow rates Fa naught to the final molar flow rates Fa, dFA upon minus Ra, right? So when we integrate these, so how we write the limits? So I will make you understand from 0 to W, which means here you can see at the initial length of the backbed reactor, where the length is equalized to 0, where we are having the initial volume V naught is equal to 0. So where we are having the 0 weight of catalyst present at the inlet part, right? In the inlet part, this part, okay? So for those reasons, we are starting from 0 to W. Now, how W came? Now, after after the completion of the entire volume and the length of reactor, at the outlet part, we have this much mass of catalyst. All the blue circles indicate the mass of catalyst, solid catalyst, which is present in the entire packed bed reactor. So here at the final length, where the length of reactor will be equal to the final length of the reactor, where we have the complete volume of the entire packed bed reactor filled with the mass of catalyst, right? Mass of the catalyst, okay? Entire total mass of the catalyst, which is indicated by W, total weight of the catalyst filled in the hollow space of the tubular reactor. And so we have the packed bed reactor, right? So total weight of the catalyst which is filled in the packed bed reactor is indicated by W. So for those reasons, we are writing W, right? So limits are from 0 weight to the final weight W, right? So integration of 0 to W dW is equal to dFA by minus RA. So from initial molar flow rates to final molar flow rates of reactants, initial molar flow rates is indicated by FA naught, and final molar flow rates is indicated by FA, right, with respect to the species reactant A, right? So when we integrate this, integration of dW from 0 to W, so we'll remain with the W minus 0, which means W is equal to integration of FA naught to FA dFA by upon minus RA, right? So here we have derived the design equation of the packed bed reactor, right? But we need to understand now, when we apply the equation 9, the design equation of the packed bed reactor, in order to calculate the weight of the catalyst, right? So W indicates the weight of the catalyst. So we need to ensure certain conditions when only we can apply the equation 9, right? The conditions are, these are the important two conditions: when there is no pressure drop and when there is no catalyst decay. During those both conditions, we can use the design equation number 9, right? So by using this design equation, when there is no pressure drop and when there is no catalyst decay, right, these both conditions only, we can use this integral form of design equation of the packed bed reactor, okay? So by using this integral form of the packed bed design equation of the packed bed reactor, we can calculate the amount of weight required to reduce the initial molar flow rates, from FA0 to FA, right? The amount of catalyst, the amount of solid catalyst which is required to reduce the molar flow rates of reactant from FA0 to the final molar flow rates of FA, right? So by using this equation, we can calculate how much amount of catalyst is to be required in order to achieve the desired conversion and the desired product efficiency, okay? I hope you understood. Now we'll understand these figures, right? We already understood in the plug flow reactor, so same figures will be applicable to the packed bed reactor, right? So this figure indicates the profile of the molar flow rates, how the molar flow rates of reactant and product vary with respect to the length, volume, and weight of the catalyst present in the packed bed reactor, right? So let's say here we can see at the inlet part, where we are having the higher concentration of the reactant species, right? So we are starting from here, right? So at the inlet part, in the case of product, this is the reactants and these are the products, right? So at the inlet part, we are having the no products, right? Because the reaction has not started, due to which we have 0 product present at the inlet part, right? So at the here, in the case of reactant, where we at the inlet part, where we are having the maximum amount of reactant concentration present at the inlet, right? So what will happen? As the reactant will flow through the entire packed bed reactor, the reactants will get converted into new chemical species, and those new chemical species will get converted into the products, final products, right? So we are having the higher concentration of the reactants in this much area, right? So due to the higher concentration of reactants, we'll have the higher rates of reaction. Due to the higher rate of reaction, we'll have the steepest slope, due to which we have the higher rate of concentration present in the inlet part. We'll have the higher concentration of reactants. So higher concentration of reactants will react with the active sites present on the catalyst and will get converted into the new chemical species and the new products, right? So due to which we have the drop of the concentration, decrease, the concentration of reactants drastically decrease, right, indicated by the steepest slope, right. And after certain weight of the catalyst, length and weight of the catalyst, these become saturated, which means in this part now we have no more reactants present in this weight of the catalyst, right. From in these positions we are having no more reactant presence, due to which all the reactants have converted into the products, right, due to which we'll come to the end of the completion of the reactions, right. So due to the completion of the reactions, the curve flatters. Okay. And same way in the case of products, at the inlet part we have no product form now, right, no product form, due to which the concentration of the products or the molar flow rates of the products will be 0, right. So with respect, so in this part, initial part of the packed bed reactor, where we are having the higher concentration of the reactants, so we'll have the higher rates of conversion of the reactants into the product, right. So drastically the concentration of the product formation will be increased, right, because in the reaction environment new products are getting generated, due to which drastically the product will get generated, and finally the curve flatters, which means here at the end of the reactor, where we have the minimal concentration of reactants or no concentration of reactants present in the end of the like the reactor, which means we have the major amount of product present at the end of the reactor, and due to which the reaction comes to the completion. Okay. And completion, due to which the curve flatters, right. I hope you understood, because the rate of the reaction is the function of temperature, pressure, concentration, catalytic activity, transport and diffusion parameters, right. I hope you understood. Okay. So in today's lecture we have understand the importance of the packed bed reactor, right, how we derive the design equation of the packed bed reactor, right. What are the difference between the packed bed reactor with the other industrial reactors. Okay. Now one last question which arise in our mind is why this bed is very important in the packed bed reactor. I hope you have the question coming into your mind, right. Why this bed is very important in the packed bed reactor, right. So in order to make you understand, we have the certain important points we need to consider, right. Why the bed is very important in the packed bed reactor, right. So first, in order to hold the catalyst at the stationary phase, right. So the bed is important, which means we need to fill the entire hollow space of the reactor with the packed with the packed solid catalyst, which means there are no empty space, or there are no void space, means there are no empty space remaining, right. We need to ensure the uniform distribution of all the solid catalysts filled in the entire packed bed reactor, right. So after ensuring that, we need to ensure we have the stationary state of the all the solid catalysts, right. So in order to achieve the stationary state of the solid catalyst, we need to ensure the completely filling of the entire hollow space of the packed bed reactor with the solid catalyst, due to which finally when the reactants will flow through the stationary solid catalyst, the solid catalyst should not get disturbed, right. So solid catalyst should not move here and there, right. So we need to ensure the solid catalysts are whole in a stationary phase, while the reactant molecules will flow through the entire packed bed reactor, right. The second important is, due to the applications of the catalyst will provide the higher internal and external surface area, right. So if we are having more surface area, which means more and higher exposure of the active sites which are present on the solid catalyst, right. So if we are having the higher surface area internally and externally present in the catalyst, we'll have the higher exposure of the active sites of the catalyst, right. So if we are having more exposure of the active sites of the solid catalyst, which means we'll have the higher rates of the reaction, right? Higher rates of the reactions. Okay, if we are having higher rates of the reactions, which means we can achieve the desired product efficiency, desired conversion in by using the packed bed reactor. I hope you've understood, right? So I am again recalling, right? If we are having the higher surface area present in the packed bed reactor, which means internally and externally, right? Higher surface area, which means we'll have the higher exposure of the active sites present on the solid catalyst, right? If you're having higher exposure of the active sites on the solid catalyst, which means we'll have the higher rates of the reactions. Due to the higher rates of the reactions, the reaction will proceed and will come to completion, and will have the major formation of the desired product, and we'll have the higher efficiency of the conversions, right? So packed bed reactor is very important. So the bed in the packed bed reactor is very important, right? Third, we need to ensure the plug flow behavior, right? Means we need to ensure all the assumptions of the plug flow reactor are applicable to the packed bed reactor, right? Okay, the fourth point is we need to ensure the uniform distribution of the heat in mass transfer through the entire volume length and length of the packed bed reactor, right? So we need to ensure the uniform heat transfer, uniform mass transfer through the entire packed bed reactor, right? There should be no not the presence of we should not have any presence of the hotspots in certain areas of the reactor, right? Okay, so we need to ensure the uniform heat transfer and the mass transfer through the entire volume and the length of the packed bed reactor, right? We'll dwell more deeper into all the significant points in the upcoming lectures, right? Fifth point is in order to provide the mechanical stability to the packed bed reactor, right? How mechanical stability? We are filling the entire volume of the packed bed reactor with the solid catalyst, which means we are trying to prevent the attrition loss of the solid catalyst, which means attrition loss means, let's say this is one solid catalyst and these are the another solid catalyst, right? So there should be no due to the tightly packed of the solid catalyst, there will be no attrition loss. Attrition loss means due to wear and tear of the solid catalyst, right? So we have the tightly packed solid catalyst, which means there will be no attrition loss present in the packed bed reactor. Now in the second case, if we are not packing tightly the solid catalyst into the packed bed reactor, which means we'll have certain space between the solid catalyst, right? Due to the availability of the certain space in the solid catalyst, when the reactant molecules will flow through the entire packed bed reactor, what will happen? There are chances of the attrition loss. Attrition loss will take place with the solid catalyst, which means both the solid catalyst will rub or will move likewise, right? And we'll have the attrition loss, means due to the wear and tear of the solid catalyst will disintegrate, will degrade, right? And the activity of the solid catalyst will reduce, right? So we should not have the attrition loss. In order to prevent this attrition loss, right, you can see these rubbings between both the hands, which will result into the disintegration of the solid catalyst present in the packed bed reactor, right? So in order to prevent the attrition loss, we should have the uniformly packing of all the solid catalyst inside the packed bed reactor, right? Okay, now with the mechanical stability, we can also ensure the higher stability of the packed bed reactor due to the uniform packing of the packing materials in the packed bed reactor. So the packed bed reactor can sustain high temperature and pressure, right? And final point is effect of pressure drop and the flow distribution. Okay, so effect of pressure drop. Okay, so let's say if we are having, okay, let's say I will make you understand very simple. Let's say if we are having the room dimension of 10 feet by 10 feet, and we have the two doors, one entry door and one exit door, right? So in the room of 10 feet by 10 feet, we have one entry door and we have exit door, right? So if in the room of 10 feet by 10 feet, we have 5 people standing, right? 5 friends are standing here. Okay, now if one new friend want to enter the room and want to get passed through the room and you want to exit from the exit door, right? So we have only 5 friends present in the room, so it will be easier for a new it will be easier for a friend to just pass through the room, and easily he can go through the exit door, right? But what if we are having the with the same dimension, if we are having 50 friends in one single room, which means it will be very difficult for a new friend to just enter the door. And for example, if he or she enters the door, but it will be difficult for that new friend to pass through the entire room, right? Because we have no remaining of the void space. If we are not having any void space, new friend cannot move in the room and cannot go through the exit path, right? which means in the peg bed reactor, if we are having the solid catalyst of, let's say, 1 inch, right? 1 inch. So if we are having the higher size of solid catalyst, which means we are having the higher void space between the solid catalyst, right? These are the solid catalysts. Let's say these are the solid catalysts. So you can see the void space between two between these, right? You can see the white space. But if we decrease the size of solid catalyst, let's say from 1 inch to 1 millimeter, right? Now what will happen? The solid void space will decrease. Due to the decrease in the void space or in the peg bed reactor, will have the effect of pressure drop, right? There will be more pressure drop, which means the molecules which are entering into peg bed reactor will have difficulty to flow through the entire peg bed reactor and to pass through the outlet stream, right? Okay, so the pressure drop plays a very important role in the contact time. If we are having the lower void space, if we are having the lower the void space, which means we are having the higher contact time, we will have the higher pressure drop, right? Higher contact time between the molecule and the solid catalyst. So the contact time of the molecules with the solid catalyst will be higher, due to which the conversion or the reaction will take place, and conversion will be more, right? Depending upon the applications, right? So these are the effects of pressure drop. We'll understand more into detail in the upcoming lectures, right? Now the flow distribution. Which means for the flow distribution, we should have the uniformly packing of the packing materials in the peg bed reactor. If the materials is not uniformly packed, right? Now what will happen? There are certain formation of the channeling. Channeling means a certain pathway, which is the pathway the molecules follows, right? There we have the higher void space. Okay, so we should not have the channeling in the idealized peg bed reactor, right? We need to prevent the channeling in the peg bed reactor. Okay, then only the peg bed reactor will follow the idealized peg bed reactor, right? So channeling means, for example, the reactant is entering into the peg bed reactor, so likewise the reactant will move, right? So these are called the channeling, right? So we should not have the channeling in the peg bed reactor, idealized peg bed reactor. We should not have the channeling, right? So what will happen? Now all the reactant molecules are not able to distribute uniformly throughout the entire peg bed reactor. So here in this case, in the case of channeling, where we can see many molecules are just passing through these path, right? It's called the channeling. So we need to prevent the channeling, right? Likewise also we have the channeling, right? So we need to prevent those channeling, right? So what will happen? All the molecules will try to just follow this path and white space, and they will exit the reactor, right? Likewise, I hope you have understood, right? So we should not have the channeling in the idealized peg bed reactor, right? Now this channeling part will comes in the non-ideal peg bed reactor, right? So we need to prevent the channeling. We need to ensure the uniformly packing of all the solid catalysts in the peg bed reactor. We need to ensure the uniform distribution of all the molecules in the peg bed reactor, right? I hope you have understood. So in order to conclude this lecture, we have understand the importance of the peg bed reactor. What is peg bed reactor? How the peg bed reactor differs from other industrial reactors, right? We have understand important assumptions of the peg bed reactor, and followed by the deriving of the design equation of the peg bed reactors, right? I hope you have understood. Okay, so if you have any query, then please feel free to comment below. I will try my best to reply to your comments. Okay, and if you want me to make a special video on different types of packing materials, you can comment below. Okay, and I will try to make a special video for the different packing materials which are filled in the packed bed reactors, right? Based on the different applications, we'll have the different shape and size of the packing materials. Okay, so until then, stay focused, keep learning, and stay curious. Thank you for watching my video. JMB.